Hello friends, in this video I'm going to show you some examples of a group. So I'm considering here two examples. First one is set of integers denoted by z with addition is a group. So binary operator here is an addition, okay. And the set is set of integer denoted by z. These two, that set of integer and addition, these two will form a group. Another one is let G be a set having four elements 1, -1, I, -I is an abelian group under multiplication. Here binary operator is multiplication, okay, and the elements are 1, 2, 3, 4. Four elements are there, finite number of elements are there. 1, -1, I, -I is an abelian group. Abelian group means the commutative property will be satisfied. In my last video I have shown you the four properties: closure, associative, existence of identity, and existence of inverse. If one more property, commutative law means a plus b. Commutative law means let me show you. If commutative law means two element is there, let a and b belongs to the set G, then a, the binary operator, b will be equals to b binary operator a. If this satisfies, then we can say that the group is abelian group or commutative group. Also sometimes we can say it commutative, commutative, commutative group, if this one satisfies. So let me show you how it works. First we are considering here set of integers. Set of integers means let Z be a set, is a set of integers is there. Okay, so I'm considering -3, -2, -1, 0, 1, 2, 3, okay, and so on going on. Okay, then let me show you first the first property, and the binary operator here is addition. As addition is a binary operator. Okay. First property is closure. First property is closure. Okay, closure means how to show a plus b. Okay, the resulting element must be in a group, must belongs to the group G. That's what we have to show for the closure. Here binary operator is addition, so any two elements, if you are considering any two elements from this set, suppose I'm considering here -3 is the one element and another element is -1. Let these two are the elements, then -3 plus -1 will be equals to what? -3 -1 is -4. -4 is again in a set Z. Then we can say that for this will be true for any set of elements. Okay, if you consider 0, first element is 0, another element is 2, okay, then also it will be satisfied. 0 plus 2 will be equals to 2, and 2 is in the set Z. Then we can say that for every set of elements it satisfies the closure property. Then we can say that the set Z having closure property. First property satisfied. Next, second property, but we are having second property, associativity. Second property is associativity. We have to associate here. Okay, let me consider three elements. First is -3, -2, and another element is, let it be 1. Then according to the definition, A binary operator star B, if we associate this one with C, will be equals to A binary operator B star C. Star here is addition, because we are considering it is given here addition, okay, with addition, so we have to consider star as a addition. Then let -3, this one here, plus B is, let it be -2, okay, make it associate. Then star again is a plus, then C is 1. Here put like this, -3, because A is -3, then star is plus, B is -2, then star is again plus, C is 1. Let me show you. Minus 3 minus 2 plus 1 equals minus 3 plus what it is, minus 1. Minus 3, this one. Okay, minus 3 minus 2, how it is, minus 5 plus 1. What we are having, minus 3 minus 1. So minus 4 equals to minus 4. These two, and again these two elements belongs to the set this one, because look here, this one represents a closure property. Under this one, closure property, this property a plus b, the element will belongs to G. This represent the closure property. Here this one will be closed, this one will be closed, means the element minus 5 must belong to the set Z. Again, if you are considering minus 5 minus 1, this again represents a closure property, because we have already proved that closure property satisfy in Z. So this element will also, the resultant of this element minus 5 plus 1, this one is minus 4, this will also belongs to the set Z. As we can say that closure property and associativity property both holds in Z. Next existence of identity and existence of inverse we have to show here. Okay. Let me consider another. Existence of identity. EXI. Existence of identity element. The identity element, we already know that 0 is an identity element. 0 is an identity element with respect to addition, because if we add any number with 0, okay, suppose minus 3 plus 0, this will again same number, minus 3. If minus 1 plus 0, this will again minus 1. 0 plus 0 again 0. So this element for any set of numbers in Z, any set of minus 2, minus 1, 1, 2, 3, 4, whatever you will take up to infinite. Okay, this one plus 0 represents the same number here. So we can say that 0 is an identity element in this set. So 0 also present here. Next one, last property, fourth property, this one is third one. Fourth property is existence of inverse element. Existence of inverse element. So what we are, existence of inverse element, which means if A belongs to the set, then there must exist some element B belongs to the set G such that A binary operator B will be equals to the identity element. Then we can say that existence of inverse element exists for every element if this thing happens. So let me consider two elements from the set Z. Two elements are let it be minus 3 and 3, which implies minus 3 and 3, which implies minus 3 binary operator plus 3, which is equals to 0. If we consider another element, like 2, okay, then 2 plus of minus 2, which is equals to 0. 1 plus of minus 1, which is equals to 0 again. So every element, so minus 3 is an inverse element of 3, or in reverse also we can say 3 is an inverse element of minus 3. 2 is an inverse element of minus 2. 1 is an inverse element of minus 1, or minus 1 is an inverse element of 1 also in this case here. So for every element we are having an inverse element. Then we can say that existence of inverse element exists here. Okay, so all four properties, what are the properties are there? First, closure property. Next one is associativity. Another one is existence of identity element. Existence of identity element with respect to addition is 0 always. And existence of inverse element. Here inverse element exists for every element. Minus 3 is an inverse element of 3. vice versa, 3 is an inverse element of -3, because if you add these two, we'll have the identity element 0. Then we can say that the set of integer z with addition as a binary operator is a group. Now look at the another example. What is given here? G. Let G be a set of elements. 1, 2, 3, 4 elements are there. 1, -1, I, -I. 4 elements are there. This is an abelian group. This set will form an abelian group under the binary operation multiplication. So I'm going to show how this will form a group under multiplication. And this one is a abelian group. Already I said abelian group means commutative law must be hold. So first we have to prove the closure property. Closure property. Let's consider what we are having. G having 1, -1, I and -I. 4 elements are there. Okay. Then first property closure. First property closure. Take any two number. Okay. Take any two number under multiplication. But look at the sentence under multiplication. So binary operator here is a multiplication. Okay, so we have to consider multiplication here. So closure, take any two number, let it be 1, -1, and multiply these two. What it will implies, 1 multiply with -1 is equals to -1. This element, resultant element, is again in a set G, -1. For another element, let it be let it be I and -I. What it would imply, I star -I, what will have, minus to I square, which is minus of -1, which is 1. 1 is again an element of the set G. So for any set of elements, their multiplication must lie in the set G. Then we can say that closure property holds in this set. Next one is associativity. Next property is associativity. Okay. Here consider any three element. Let it be 1, -1, and I'm considering here I. Okay. These three elements, make it associate. 1 star -1 star I must be equals to 1 star -1, make an association here, then again star and I. Closed, this one is closed because we have already proved this one. So 1 star -I, this will be equals to 1 multiply with -1, -1 star here and I. What we are having, -I will be equals to -I. This will satisfy for every set of elements. If you choose this and this, then also their association will be equal. Right hand side and left side both are equal. Then we can say that this one is satisfying associativity law. And the another one is existence of identity element. So what we are having, set having G equals to 1 -1 I minus I. This is a set. We have to show that existence of the third property, existence of identity element. We already know that 1 is a multiplicative identity. Nothing to show that. If you multiply 1 to any number, you will have the same number. Nothing. 1 multiply with 1 equals to 1. I multiply with 1, which is I, minus I multiply with 1, which is minus I. So 1 is an identity element. Nothing to show that. Okay. So under multiplication, 1 is an identity. So identity element exists here. Last property, last one is existence of inverse. Inverse, we have to show that. Okay. Inverse means A star B. If A is an element, there must exist B such that their multiplication yields the identity element. Identity will let it be E. Here identity element is 0, as already we have shown here. No? identity element is what? 1. Identity element is 1, so E must be equals to 1. So let me find how it will work. So first I am considering 1 multiply with 1. Okay, 1 multiply with 1, what we are having? Identity element 1. If you are considering another element -1 multiply with -1, what we are having? Minus into minus plus 1. So for 1, inverse element is 1. For -1, inverse element is -1. For I, multiply with -I, what we are having? Minus I square, which means minus I square, which means -1. What we are having? The identity element 1 here, 1 here. So minus I is an inverse element of I here. For 1, inverse element is 1. For -1, inverse element is -1. For I, inverse element is -I. Same case for -I, inverse element is I. So all 4 properties satisfies here. First one, closure. Okay, closure means under multiplication, how it comes? Any two element, consider any two element, the resulting element must be in this one. Any two element, resulting element must be in the set G. For associativity also holds here. Existence of identity also holds here. Multiplicative identity is 1. Multiply with any element, you will have the same element. And inverse element also exists here. For the for the element 1, inverse element is 1. For -1, inverse element is -1. For I, inverse element is -I. For -I, inverse element of -I is I. So all 4 properties satisfies this. Then we can say that it is an group. One more thing is given here, that G is an abelian group. Abelian groups means what we have to show? We have to show that it satisfies the commutative law also. Okay. Commutative law means how we have to show, if 2 elements are there, A star B will be equals to B star A. Then consider any 2 elements from the set this one G. Let it be 2 elements. I am considering here 1 and I. I am considering 2 element 1 and I. Then multiply these two. 1 star I will be equals to I star 1. For any set of elements, let it be -I and I. -I star I will be equals to I star -I. That will be what? Minus I square, which is equals to minus I square. Okay. Then it satisfies the commutative axioms also. Then we can say that this one is the set G with elements 1, -1, I, -1 is an abelian group under the binary operation multiplication.